Imagine spending like over $1 million in compute just to fine-tune an open-weight large language model exclusively on your company's proprietary, highly complex code base.
Oh, yeah. A total nightmare scenario waiting to happen.
Right. And at first, it works beautifully. I mean, it's generating flawless Python scripts. But then, a month later, your legal department comes in and asks you to update the model with, new localized data privacy and HR policies.
Naturally.
So you run the fine-tuning pipeline. The model learns the HR policies perfectly. But when you ask it to write a basic API endpoint,
It completely hallucinates.
exactly, it totally forgot how to code. And as machine learning practitioners, you live this nightmare.
Oh, absolutely.
It's the holy grail of deploying LLMs in an enterprise setting, right? Continual learning. You absolutely need to update deployed models with sequential streams of new data without obliterating the fundamental representations the model has already mastered.
Yeah, but you also know the standard brutal trade-off there.
Right. Either you run full model fine-tuning and suffer catastrophic forgetting, or you try to protect the model's memory by using parameter-efficient fine-tuning methods, PEFT.
Which inevitably cripples the model's expressive capacity over time. It's the classic plasticity versus stability dilemma.
Exactly.
I mean, we need models plastic enough to absorb diverse, highly specific new tasks, but stable enough to retain the fundamental architectures of their previous training.
Right. And right now, the entire industry is largely stuck, like compromising on one side of that spectrum or the other.
Yeah, often relying on incredibly complex engineering workarounds that just do not scale well in production environments.
Which brings us to today. Today's deep dive unpacks a breakthrough paper from Red Hat AI Innovation and the MIT IBM Watson AI Lab.
Sculpting Subspaces.
Yes, Sculpting Subspaces. Constrained full fine-tuning in LLMs for continual learning. We're going to explore how the authors achieve state-of-the-art continual learning by dynamically identifying and updating task-specific low-rank parameter subspaces via singular value decomposition.
And the kicker for anyone managing a cluster of GPUs right now.
Zero additional parameter overhead.
Yep. They accomplish this with zero additional parameters. It's wild.
Okay, let's unpack this. Because existing methodologies are hitting a very serious mathematical and architectural wall right now.
They really are.
We really need to break down the mechanics of why current SOTA methods fail before we can appreciate the geometry of this new solution.
Well, looking at the current paradigms, they broadly fall into two camps.
Okay.
First, we have the parameter-efficient methods, things like LoRA and its continual learning variants like O-LoRA and enf-LoRA.
Right.
These methods attempt to solve the stability problem by isolating parameter updates to very small, newly initialized parameter subspaces. The core weights of the transformer are just frozen.
Which, by design, does a decent job of mitigating catastrophic forgetting.
Exactly, because the original network remains untouched. However, you are fundamentally restricting the update space. The model literally cannot alter its core representations to accommodate complex new patterns.
Plus, from an infrastructure perspective, you're adding new parameters for every single task.
Oh yeah, the bloat is real.
At an enterprise scale, where you might have dozens or hundreds of sequential tasks flowing into a system over a year, that causes significant memory footprint bloat. But more importantly, it causes serious inference latency if you have to dynamically swap adapters in and out of GPU memory, depending on what the user's prompt is.
Right, the scalability is severely bottlenecked by memory bandwidth during inference.
Yeah.
Then, on the other side of the spectrum, you have model merging techniques, like ties or slurp.
Oh, right.
In this paradigm, you fine-tune full, independent copies of the model separately for each individual task.
Which sounds expensive.
It is. Then you attempt to mathematically merge the weight matrices back together to resolve parameter conflicts post hoc, usually by looking at the sign and magnitude of the updates.
Which is just computationally brutal.
Yeah, it really is.
Maintaining multiple 70 billion parameter model copies in memory during the training phase, and then running complex interpolation matrices over long sequences of tasks, it just doesn't scale.
Not at all.
If standard full fine-tuning is like trying to write a new chapter in a book by writing directly over the old words.
Yeah, perfect analogy.
And POT is like restricting yourself to just scribbling notes in the margins. The question is, how do we get the right to write on the full page again without erasing the past?
Well, what's fascinating here is the paper's core premise, which is that network weight matrices, especially in massive transformers, contain an unbelievable amount of redundancy.
Like unused space.
Exactly.
Yeah.
We do not actually need to initialize new parameters, And we don't need to restrict our optimization to the margins. We just need to geometrically constrain how the optimizer navigates the existing parameters.
Oh, okay.
The authors point to recent rigorous research showing that many parameter directions within these massive matrices basically contribute minimally, or even not at all, to the overall performance of the model on any given task.
So the capacity is already there, it's just sitting idle in the matrix.
Precisely.
Which brings us directly into the linear algebra of their proposed geometric solution, adaptive singular value decomposition, or adaptive SVD.
Right.
We are moving away from the structural limitations of adapters and getting into the actual physical geometry of the weight matrices themselves.
Yeah, so singular value decomposition acts a bit like a mathematical prism.
Okay, break that down for us.
If you apply it to a given weight matrix in a transformer layer, it splits that complex, chaotic matrix into clean, distinct orthogonal directions. It gives you the singular vectors, and it ranks them by their singular values.
Which is essentially their importance or variance, right?
Exactly. And the authors separate these vectors into two distinct components, a high-rank subspace and a low-rank subspace.
Okay, let me visualize this. The high-rank subspace, which corresponds to the large singular values, that contains the critical load-bearing knowledge from all the pre-training and all the previous tasks.
Right, that is the structural foundation.
And the low-rank subspace, corresponding to the very small singular values, represents the minimal contribution directions. It's the unused capacity of that specific layer.
That is the core division, yeah. So when the model is presented with a new task to learn, the gradient updates calculated by the optimizer are not just applied blindly.
What happens to them?
They are orthogonally projected only onto that low-rank subspace. The system calculates the full gradient, but before updating the weights, it physically strips away any component of that gradient that aligns with the high-rank load-bearing subspace.
Wait, I have to push back here, or at least play devil's advocate for the engineers listening.
Go for it.
If we are projecting full parameter gradients onto these lower singular vectors and overwriting them, are we absolutely sure they are empty of useful task data? Like, aren't we risking silent data corruption of the older tasks? Calling a subspace low-ranked doesn't magically guarantee it contains zero critical features from a task the model learned, say, 6 months ago.
It's a great question. And the authors anticipated that exact skepticism. They didn't just rely on mathematical intuition. They empirically validated the safety of overwriting these spaces.
Okay, how?
They ran extensive ablation tests on the Granite 8B architecture. To test the load-bearing nature of the subspaces, they isolated the multi-layer perceptron down projection matrix, specifically at layer 34.
Right.
Using data from a previously learned task, they systematically pruned the low singular vectors to see when the model's memory would actually break.
Okay, but hitting high pruning percentages on a single layer is a great academic exercise, sure, but what does that look like in terms of actual model degradation on a real benchmark?
Well, they pruned 99% of the low singular vectors in that specific layer. They completely zeroed them out.
99%.
And when they evaluated the modified model on the open LM leaderboard benchmarks, they saw zero performance drop.
Wait, zero?
Zero. Let me emphasize that. The L2 norms of the matrix vector products for those low singular directions were practically flatlining. The low-rank space truly is highly redundant and remarkably safe to overwrite. The critical representations from the old task data reside almost entirely in the span of the high singular vectors.
That is wild to think about. 99% pruned with absolutely no degradation in reasoning capabilities. It really reframes how we think about parameter efficiency.
It really does.
To understand the orthogonal projection, I actually like to use a spatial analogy.
Let's hear it.
Imagine the high-rank space. The foundational knowledge is the X and Y axes on the floor of a room. All your old furniture is perfectly arranged on that floor.
Okay.
The low-rank space is the Z-axis, the vertical space above the floor. Now, if you just apply a standard gradient update, it might have an X or Y component. It will slide across the floor and knock over your furniture. Catastrophic forgetting.
Right, a total mess.
But by forcing the gradient to be orthogonal to the high-rank space, you are mathematically zeroing out any X or Y movement. You are forcing the model to build shelves straight up the Z-axis. You utilize the empty room without touching the existing foundation.
That analogy actually captures the exact mathematical enforcement happening during the backward pass perfectly. The optimizer is physically blocked from stepping into the spaces where old knowledge lives.
But that immediately raises a massive logistical problem, doesn't it?
Which is?
If we are splitting weight matrices into high and low rank across a massive 70 billion parameter transformer, how do we decide the exact threshold for every single layer?
Yeah.
We know the architecture isn't homogeneous. A fixed rank cutoff across the entire network isn't going to cut it. Some layers are doing heavy computational lifting, others are basically just passing data forward.
Exactly. A fixed rank strategy completely fails to capture layer-wise variability, which is why prior attempts at orthogonal projection often underperformed.
So what's the fix?
This is where the adaptive part of adaptive SVD comes in. The authors developed a dynamic layer importance metric to solve this. Before calculating the rank threshold, they run a small sample of data from the previous task through the network.
Ooh.
For every single layer, they calculate the cosine similarity between the layer's input activations and its linear outputs.
Okay, let's break down the intuition behind that cosine similarity for a second. If the input vectors and the output vectors of a specific transformer layer have a very high cosine similarity, what is that layer actually doing?
Well, if the similarity is high, the layer is primarily preserving and routing information. It is not fundamentally changing the vector direction in the latent space.
Right.
These routing layers are absolutely critical for maintaining previously learned features. Right. They are the highways moving the foundational knowledge to the output heads.
But if the cosine similarity is very low, it means the layer is aggressively transforming the representations. It's doing heavy computational lifting, dissecting, and altering the features.
Exactly.
I like to think of the layers in a transformer as workers on a factory floor.
Okay, yeah.
You have your couriers. Those are the routing layers with high similarity. They just carry the delicate, pre-assembled packages across the floor without altering them. Then you have your chefs, the transformation layers with low similarity. They are aggressively chopping up and changing the ingredients. You want to freeze the paths of the couriers so they don't drop the old packages, but you want to give the chefs maximum flexibility to adapt to the new menu.
That factory floor analogy perfectly aligns with their rank allocation strategy.
Yeah.
Mathematically, they translate the cosine similarity into a retention fraction for each specific layer.
Right.
They define a minimum retention ratio and a target maximum retention ratio. High importance layers, your couriers, get a retention ratio pushed closer to the target maximum.
Meaning a massive chunk of their singular vectors is locked into the high-rank subspace, protecting those routing pathways.
Exactly. And low importance layers, your chefs, have their retention ratio drop closer to the minimum threshold. This artificially expands their low-rank subspace, providing the optimizer with a massive orthogonal void to learn the new task representations.
It is a highly elegant geometric routing system. You basically map the computational graph, find out who is doing the transforming and who is doing the routing, and assign the z-axis space accordingly.
Right.
But, you know, as ML expert, our listeners are probably waiting for the rigorous mathematical proof here. We intuitively understand why preserving top singular vectors sounds like a good idea for stability. But why does it mathematically equate to preventing catastrophic forgetting? Let's look at the actual loss landscape.
Yeah, we need to dive into the appendix of the paper for this specifically, Appendix A.1, which provides the theoretical backbone, the second-order Taylor expansion of catastrophic forgetting.
Okay, let's get into it.
Let's assume the loss for a previously learned task is currently resting at a local optimum. Because it's at an optimum, the first-order gradient term is effectively zero.
Right.
Therefore, any shift in the loss, any forgetting, is entirely dominated by the second-order term.
The Hessian.
The Hessian, yes.
Yeah. The change in loss is approximately bounded by the quadratic form of the parameter update vector and the Hessian matrix of the loss function.
Exactly. So visualize the loss landscape as a highly complex terrain. The local minimum where your previous task lives is a deep, narrow canyon. The floor of the canyon is relatively flat, but the walls are incredibly steep.
Okay, I can picture that.
The Hessian matrix describes the curvature of this canyon. The directions of highest curvature, the steepest walls, correspond precisely to the largest eigenvalues of the Hessian matrix.
Right.
If your parameter update takes a step up those steep walls, your loss on the old task spikes immediately and violently. That is catastrophic forgetting quantified. To minimize forgetting, you absolutely must avoid updating parameters in the directions of the largest Hessian eigenvalues.
Here's the problem, though. Computing the exact Hessian matrix or even trying to approximate its eigendecomposition for a 7 billion parameter, let alone a 70 billion parameter LLM, I mean, that's completely intractable.
Oh, completely.
The compute required would outstrip the fine-tuning itself by orders of magnitude. We can't actually map the canyon walls in practice.
No, we cannot compute it directly. But if we connect this to the bigger picture, we don't have to.
Why not?
The authors leverage crucial empirical evidence demonstrating a robust mathematical correlation between the largest eigenvalues of the Hessian matrix and the largest singular values of the network's weight matrices. They map to the exact same directions in the parameter space.
Oh, that is the crucial link. The SVD technique isn't just a clever heuristic. It is an incredibly efficient, mathematically sound surrogate for mapping the steepest, most dangerous walls in the loss landscape.
Yep.
So by locking down the high-rank singular vectors, you are functionally blocking the optimizer from stepping into the high-curvature Hessian directions. You are forcing the updates to travel strictly along the flat floor of the canyon.
And this ties perfectly back to the layer importance metric we just discussed. Empirical studies show that layers with higher input-output similarity, your couriers, exhibit significantly greater overall Hessian curvature.
They have steeper walls.
Exactly. So by allocating more rank protection to those specific routing layers, the adaptive SVD method directly minimizes the theoretical upper bound on catastrophic forgetting. It beautifully bridges the ideal yet intractable second-order optimization theory with a scalable first-order practical reality.
Theory is great, and the math definitely checks out. But in this field, theory only gets us so far. How does this actually perform when the rubber meets the road?
Let's look at the numbers.
Because in an enterprise environment, you aren't just teaching a model one or two new tricks. You are teaching it a continuous sequence of tasks. We need to benchmark this against the absolute state-of-the-art baselines like O-LoRA, especially when the sequence gets long enough to normally just shatter a model's memory.
Well, the empirical triumphs here are substantial, and they tested it rigorously. They evaluated the method on both an encoder-decoder model, specifically T5 large, and a decoder-only architecture, LAME27B. To test the limits of memory retention, they ran an extended 15-task sequence benchmark. Standard continual learning methods typically collapse under a 15-task sequence due to compounded approximation errors.
I am really curious to hear how it held up against O-LoRA, which is specifically designed to isolate task updates. Like, does the full model expressivity actually translate to higher accuracy here?
It does. On the 15-task sequence with T5 large, the adaptive SVD approach achieved a 71.3% average accuracy across all tasks.
O-LoRA.
The current parameter-efficient state-of-the-art O-LoRA hits 69.6%.
Wow.
So adaptive SVD outperformed the leading adapter method while maintaining full model expressivity and adding literally zero new parameters to the architecture.
I mean, a 1.7% bump on a 15-task sequence is highly non-trivial. It proves the stability. But what about task complexity? Text classification is one thing, but what happens when you introduce diverse reasoning tasks? Things that require deep transformations of the latent space, like coding or arithmetic reasoning.
For that stress test, they used the trace benchmark with Llama-2 7B chat. Trace evaluates instruction-tuned models on highly diverse sequential tasks, spanning multilingual understanding, complex arithmetic reasoning, and code generation.
Right.
This is where the expressivity limitation of KIOF2 really shows. On Trace, adaptive SVD hit 48.4% average accuracy, compared to O-LoRA's 41.3%.
A full 7.1% absolute improvement.
Yep.
That basically indicates that forcing the model to write in the margins with LoRa's adapters fundamentally restricts its ability to learn complex reasoning patterns. It needs the full paid.
Furthermore, and this is perhaps the most impressive metric to me, adaptive SVD demonstrated a positive backward transfer of 7.1%.
Wait, really?
Yes. This means that learning new tasks actually improved the model's performance on the older tasks it had already learned.
That's incredible.
The orthogonal updates in the low-rank space were generalizing to improve the structural foundation. Meanwhile, standard sequential full fine-tuning without SVD completely collapsed on the exact same benchmark, showing a catastrophic negative 8.3% backward transfer.
Positive backward transfer is the holy grail. The model is actually building a more robust worldview as it learns sequentially rather than just compartmentalizing.
Exactly. And importantly, for anyone deploying these models to production, the adaptive SVD model retained its general linguistic safety and helpfulness.
Oh, that's huge.
In head-to-head qualitative evaluations against the base LAME2 model, the continually learned model did not degrade into generating toxic or unhelpful outputs.
Which is a massive problem when models are subjected to unconstrained sequential updates. They so often lose their initial alignment tuning.
But here, the orthogonal projection protects the alignment vectors just as effectively as the knowledge vectors.
We also need to look at the ablation studies, because in papers like this, the ablations prove why the specific, highly engineered geometry of the method is so vital.
Very true.
What happens if we remove the orthogonal projection constraint entirely? Like, let's say we just freeze the high-rank singular vectors to protect the old knowledge, but we allow the optimizer to update the low-rank singular vectors unconstrained without mathematically forcing them to stay completely orthogonal to the high-rank space.
Well, if you remove that strict orthogonal projection constraint during the backward pass, the low-rank updates inevitably drift during optimization.
They drift.
The gradients bleed, they slowly drift back into the high-rank subspace, and they overwrite the protected knowledge. It is mathematically unavoidable without the hard projection step.
The numbers on that specific ablation are staggering, by the way. The authors demonstrated that removing the projection constraint caused the average accuracy to plummet from 79.6% all the way down to 31.2% on a 5-task benchmark.
It just completely falls apart.
So what does this all mean? It means the orthogonal projection isn't just a nice-to-have regularization feature. It is the absolute load-bearing pillar of the entire methodology. You cannot just freeze weights. You have to actively project the gradients away from them.
Exactly.
Furthermore, if you mess with the adaptive rank allocation, if you have the minimum and target retention ratios to be more aggressive and free up more space for the new task, the performance still drops by over 28 percentage points. You absolutely have to respect the layer-wise Hessian curvature.
Which raised an important point during the review of the paper. The success of the method hinges entirely on precisely identifying the boundary between signal and noise for every individual layer and strictly enforcing the orthogonal isolation of the updates.
Right.
The adaptive cosine similarity metric is really the only way to accurately find that boundary.
Let's summarize the core takeaways for you, the practitioner. If you are sitting there managing a cluster of GPUs and dreading your next scheduled model update, this paper provides a real roadmap out of the current bottlenecks.
It absolutely does.
For a long time, we have accepted the compromise that continual learning requires either boxing our models in with hundreds of adapters, or sacrificing their past memory, or building incredibly fragile model merging pipelines. Sculpting subspaces mathematically proves that you can achieve the plasticity of full model fine-tuning with the rigorous stability of parameter-efficient methods.
By leveraging adaptive SVD, based on layer-wise input-output similarity, you can dynamically quarantine the critical knowledge of the past in high-rank subspaces.
Right. Simultaneously, you can continually teach the model complex new reasoning tasks in the orthogonal low-rank voids. You maintain a fixed, zero-overhead parameter footprint no matter how long the sequence of tasks gets. We finally have the right to write on the whole page again because we learned how to mathematically write between the lines of the old text.
This raises an important question, though. Stepping back from the immediate engineering applications, it really makes you reconsider the very nature of the multi-billion parameter architectures we are building today.
Oh, for sure.
If LLM weight matrices naturally contain such a vast, continuous supply of unused low-rank capacity, they can be infinitely repurposed for sequential tasks via orthogonal projection.
Does this imply that the physical size of our current models is vastly over-provisioned during the pre-training phase? We're deploying 70 billion parameter models, but if 99% of a layer's singular vectors can be pruned with zero performance drop to make room for new data, are we only just now, through geometric techniques like adaptive SVD, beginning to tap into the true staggering information density of these latent spaces?
It's a fascinating question.
It really is something to consider as you build your next training pipeline.